This is a picture of James Clerk Maxwell. What's interesting to note about this is that, and I can't remember what book I read this in, but there was some biography or something like that, or scientific history, where basically James Clerk Maxwell was brilliant but incomprehensible. He would give these talks, and people would go and try to understand what he was saying, and they just couldn't. His school friend, Lewis Campbell, actually went through his papers and formulated his thoughts into these four basic laws. Okay, now these are differential equations. This thing here is actually an operator. Okay, when it's like this, when it's this dot that, this is actually divergence. Right, this is divergence, and then this is curl. Okay. And divergence is the notion that the vector field is diverging from a point. Okay, so let's look at the first one. This is basically, remember how we said that electric field is what, KQ over R squared or something like that, right? If we have a charge here, that the electric field comes out like that, right? Well, this is it, right? This is the divergence of it is the electric flux leaving a volume is proportional to the charge inside of that volume, right? Okay, and the electric flux, of course, would be the electric field times the area. And so if you go electric field times 4 pi r squared, that would be your divergence of that, right? And then that's equal to the charge over the air over epsilon naught. And then you can very quickly turn that into this, right? By dividing by the r squared, and you'd get the E. Okay, so this is the Coulombs Law. Is basically that, right? Just multiply it by a charge. It is also this idea of this thing here, right? So we've already seen that one. This one says that the divergence of a magnetic field is 0. Okay, another way to say that is that magnetic fields always loop. They're always loops. Okay, there is no such thing as a magnetic monopole. So there's no such thing as an isolated north pole from which the magnetic field lines emanate, right? It's always that we have a north and a south, right? And that these field lines will go whoop like this, right? Like that. And so if we have any surface, we'll have as many field lines entering the surface as we have leaving the surface. Okay, and it always adds up to 0. Okay, so another way to say it is that there's no magnetic monopoles. Okay, this one, the astute observer, this is curl. Okay, let's take a look just for kicks. Let's look at this page here, right? So this is somebody who thinks it's Harvard or something like that, right? This is a vector field that has curl. That is, if I take if I do a circular path in this, there's definitely the vector is in the direction of that path. This could be the magnetic field around the wire. Okay, this is a vector field that has divergence. Okay, a positive divergence, right? If I draw a surface here, right, the vector field emanates from that surface. Okay, so this is saying that the curl of electric field, basically the EMF, right? Okay, is proportional to the rate change of magnetic field. So this is Faraday's law, right? This is the induction. This is the chapter. This is what we're doing right now. Okay. And then this thing here, this is the curl of magnetic field. So we're saying that if we have a current like this, that the magnetic field curls around that wire. Okay. So this is Ampere's law. Okay. Now notice that it's not just the curl of the magnetic field isn't just the current, which is what this guy is. There's also this term in here. Okay. And Maxwell threw this term in here. This is intriguing. It's also saying you can have just plain old current, which is, I don't know why it's a J, right? Okay. But you can also have a changing electric field. This is sort of like, Maxwell's ghost, right? Okay. So just consider this, okay? Imagine that this is a capacitor. The capacitor is not charged. We've got a resistor. We close the switch. For some period of time, a current is going to flow, right? Until this capacitor is charged, and then it stops flowing, right? So in this case, a charging capacitor is going to have a current that goes like that, right? Current over time, right? Well, while the current is flowing, there definitely is a magnetic field. This magnetic field is going to be around these wires, right? And it's going to be into the page on this side and out of the page on this side, right? Because we know that right-hand rule, put our thumb in the direction of the current, okay? But what if we have a capacitor like this? What about right here? Is there no magnetic field here? Because there certainly isn't a current across the capacitor, right? And so, is there no magnetic field? Magnetic field here, but no magnetic field where this capacitor is? Because remember, this is a capacitor too, right? I have these plates, and they could be 5 meters apart. It's not a very good capacitor, but it would charge, right? Some current would flow to charge this capacitor. Okay, is there a magnetic field around this? Right? Well, Maxwell said, yeah, the nature is continuous, right? There would be a magnetic field here. So there's like a virtual current here. So what's going on there? Well, a lot of nothing as far as charge transferring, but what's happening is you're getting an electric field that's going from nothing to there is an electric field, right? And so if you look back at this thing, right, this is the rate change of electric field. That's what's going on there. Is that inside this space here, there's an electric field that's changing. So a changing electric field has a magnetic field around it, right? Do you suppose that's how light works, right? You have a changing magnetic field creates or changing electric field creates a magnetic field. Magnetic fields create electric fields. Yeah, through empty space. Anyway, just the thing to think about, right? All right.